Here, there are objectives for determining freezing time. First, to describe the temperature history at the center of solid and liquid food. Second, to explain the effect of different process condition, product size, and air velocity on the freezing time. Third, to compare the freezing time calculated using Planck method with those obtained from the experiment.
The results for the first experiments shows that the sample with diameter 5 mm and the length 10 mm and air velocity 1 meter per second with the starting temperature 20 degrees C and ending temperature negative 18 degrees C. From the paragraph, it shows that the sensible heat of water remains constant at 0 degrees C, while potato sensible heat remains constant at negative 2 degrees Celsius. At the freezing point, as the substance changes from liquid to solid, its temperature remains constant even though heat is being removed. This is because the added heat energy is being used to break the intermolecular bonds in the liquid and convert it into a solid. This process occurs at a constant temperature until all the liquid has solidified. The flat line indicates that even though heat is being removed from the substance, its temperature does not decrease until the phase transition is complete. Once all the liquid has turned into solid, the temperature will begin to decrease again as more heat is removed from the solid.
Result 2 shows that temperature versus time for 10 multiplied by 20 mm dimension of potato and water with 5 meter per second air velocity.
Result 3 shows a graph of temperature versus time for 5 multiples by 10 mm dimension of potato and water with 10 meter per second air velocity.
Results 4 shows the graph temperature versus time for 10 times 20 mm dimensions of potato and water with 1 meter per second air velocity.
Result 5 shows that the temperature versus time for 5 multiple by 10 mm dimension of potato and water with 5 meter per second air velocity.
Last, for result 6, the graph shows that temperature versus time for 10 multiplied by 20 mm dimension of potato and water for 10 meter per second air velocity.
This experiment involved obtaining freezing time when the center temperature decreased to negative 80 degrees Celsius. Temperature time data were obtained for each trial and 6 graphs were created for similar operating conditions. The operating conditions that were adjusted were the diameter, length of the product, and air velocity. Based on all the 6 graphs of temperature versus time for potato and water, we can indicate that as the time increases, the temperature of both potato and water decrease. Both temperature of water and potato decreases to the freezing point as sensible heat is removed. It was observed that samples with higher water content, which is water, tend to freeze more rapidly than samples with lower water content, which is potato. From the graph, it shows that the water starts to freeze at 0 degrees Celsius, which aligns with the principle of freezing point of water, while the potato starts to freeze at below 0 degrees Celsius due to the presence of solids in it. Water has a high thermal conductivity, which facilitates the heat transfer and accelerates the freezing process. The temperature of water remains at the freezing point until a complete phase change occurs as latent heat of fusion is removed from the water and convert it to solid ice. For the potato, the latent heat is removed a bit faster with decreasing temperature. As water in potato converts into ice, the remaining water becomes more concentrated with solids and depresses the freezing point. Lastly, most sensible heat is removed until freezing temperature, negative 80 degrees Celsius, is reached. Next, time taken for 5 times 10 dimension of potato and water to achieve negative 80 degrees Celsius freezing point is shorter than 10 times 20 dimension of potato and water. This is because the surface for area per unit volume of 5 times 10 dimension of potato and water is larger than 10 times 20 dimension of potato and water. Thus, heat is lost more quickly from 5 times 10 dimension, which will lead to more effective heat transfer and faster freezing than 10 times 20 dimension.
According to the data we acquired, the freezing period for water with a 5 mm multiplied by 10 mm is 5.0704 minutes when the air is traveling at a speed of 1 meter per second, and it is 2.427 minutes and 1.787 minutes when the air is moving at 5 meter per second and 10 meter per second respectively. When the velocity is 1 meter per second, the freezing time for the size 10 mm multiplied by 20 mm likewise falls from 14.7158 to 7.1484 minutes. We can conclude that increasing the air velocity can decrease the freezing time, as the increased movement of air around the product will help to remove heat more quickly.
Question A. Discuss how the center temperature changed with time for samples of water and potato. Comment on the shape of the plot. For a sample of water, the removal of sensible heat caused the temperature of water to drop to the freezing point from 20 degrees Celsius to 0 degrees Celsius. Due to the elimination of latent heat of fusion, the temperature in the constant phase will stay at the freezing point until the phase transition is complete. Ice will form from the liquid water. The absence of the sensible heat will cause the ice temperature to drop quickly. While for the sample of potatoes have a lower freezing time than water due to the solids in food and the fact that latent heat is released more quickly than in water. When the temperature drops, the first nucleation takes place and ice crystals start to form. As a result, the potato will mix with the ice and solid ingredients. Until the endpoint temperature is attained, the sensible heat will be removed. Discuss the effect of air velocity on the freezing time. The answer is when air velocity increase, the freezing time will decrease. This is attributed to the increase in heat transfer coefficient at increased air velocity. When the air velocity increase, it will facilitate a more efficient transfer of heat from the frozen substance to the ambient air. As a result, the substance will lose more heat quickly, which will speed up the freezing process. Thus, the freezing time will decrease.
The answer for the last question is that the freezing time of the food sample are different compared to the freezing time that was calculated using Planck equation. The first table shows the comparison between experimental freezing time and Planck equation freezing time of water, while the next table was the comparison of freezing time of potato. The freezing time of an experiment may differ from prediction based on the Planck equation due to various factors such as experimental condition, environmental influence, or specific characteristic of material involved. Planck equation provide theoretical insight, but real-world experiment can be influenced by practical consideration and uncertainties. It is important to consider the specific detail of the experiment and the condition under which is why it was conducted to understand any variation from the theoretical expectation. This is how the freezing time of water with 10 mm diameter were calculated using Planck equation, and this is how the freezing time for potatoes with the area 5 mm were calculated by using the Planck equation.